What we're going to do now is we're going to talk about, we're kind of moving into the area where we're almost done, so we got to finish up some odds and ends. This particular time, we're talking about oscillations. Next week we'll get into sound, and there are two major types of oscillations that we're concerned about. There is the spring pendulum, and then there is the simple pendulum. So a spring pendulum, if you have a mass at the end of a spring, you pull and it's hanging, you pull it down, you let it go, and it goes bouncy, 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 up and down. You have a spring on a smooth floor with a mass, you pull the mass back, it bounces back, bouncy, bouncy, bouncy. So stuff that looks like this, that oscillates back and forth. A simple pendulum is, you can think of a simple pendulum as like everybody's got a grandfather clock or a grandmother clock or just a clock with a pendulum, basically a mass at the end of a long stick, and it goes back and forth. Person on a swing, all sorts of things are can be used as a type of simple pendulum. Now, we are familiar with rotational motion and the terms frequency and period. Frequency, capital F, has units of inverse seconds or hertz, whereas the period, we use capital T in seconds. Whereas frequency is the number of oscillations in 1 second. The period is the amount of time for one oscillation. And I'll shorten it down into OSC, because I'm not fond of writing. For a spring pendulum, the period is 2 pi m over k, where m is the mass, k is the spring constant. A simple pendulum, the period is 2 pi L over G, where L is the length of the pendulum and G is gravity. Now let's look at each of these individually. For a simple pendulum, period 2 pi L over G, and then since frequency is the inverse of period, it's 1 over 2 pi G over L. And you sit there, and when when you look at these equations and you go, is it L over G or G over L? I don't really understand. This is how you obviously, I mean, a lot of times I go, I don't know, 2 pi G over L, L over G. I'm kind of confused. What you normally do is, you know, the units for period are seconds. That's just obvious. Well, you can do a unit check. Let's assume incorrectly that the period is gravity over length, square rooted. Gravity is meters per second squared, and L is in meters. So if we just do that, well, that meter will cancel with that meter, and I'm left with 1 over second squared, which is 1 over second. So that isn't the way that you would arrange period. You would arrange period in the other way. This obviously deals with frequency because you have inverse seconds. So when in doubt, do a quick unit check. Another thing that we can look at is that period is length dependent, gravity dependent, because L and G are in the equation. So if you increase L, the period increases. If you increase the gravity in which it's operating, you decrease the period. It is. Now, one of the things that we can look at, and this is a question that shows up on multiple choice tests, you have a simple pendulum. You quadruple the length. What happens to the period? Excuse me? We're not up to the trick question yet. It doubles. Let me show you how. So T prime, the new period is 2 pi square root of L pi over, or L prime over G. This is 2 pi 4L over G. L prime is equal to 4L. This square root of 4L, you can change it so that it is 2 times 2 pi square root L over G, and it becomes 2 times the old period. So that lets you know how to figure out, if you adjust something, how is the other variable changed. Now here is a trick question. If I quadruple the mass on that simple pendulum, how is the simple pendulum's period affected? It's not affected at all. There's no mass in the period equation for simple pendulum. It is mass independent. A lot of people, when you say, oh, you quadruple the mass, what happens? And they go, well, it affects the period. No, according to physics, it doesn't. Now, if there's air drag, stuff like that, you could have a mouse at the end of a 20-meter pendulum. You can have an elephant at the end of that pendulum. But, now granted, the air friction would affect it. But the overall, the period is the same for both, as long as the effective length of the period or the pendulum remains the same. So let's say we had simple pendulum oscillates 50 times in 150 seconds. What is the length if you are on Earth? So Earth, G is equal to 10. So the simple pendulum oscillates 50 times in 150 seconds. What is this? Now, the total time is the number of oscillations times the period. So if it took 2 seconds to oscillate once, and if it oscillated 10 times, then you would need 2 times 10 or 20 seconds. So this becomes T equals N 2 pi L over G. I'm looking for L. Square root or square everything. T squared equals N squared 4 pi squared L over G. This means GT squared over 4 pi squared N squared is equal to L. And this gives you 10, 150, 4 pi squared, 50 squared. So the length is going to be big. Oh, it's not that big. 2.28 meters. Second question, what's T if this pendulum is on the moon? So the period of the pendulum is now on the moon. What is it? The period does change because gravity changes. Gravity of the moon is 1/6 that of Earth, or 10/6. So this becomes 2 pi square root 6 times 2.28 divided by 10. And now you have the period. .35 seconds. So that just uses some basic manipulation of pendulums. Simple pendulums. Yes? Well, gravity is now 10 meters per second divided by 6. Yes. Because, I know what you're getting at. G sub m is in the denominator. So 1 over G, leave it to my pen at that moment to 1 over G sub m is 6/10. And so that is a simple pendulum. The most important thing is probably understanding that, and then these in terms of potential multiple choice questions, etc. Okay, now back to the other type of pendulum, or the spring pendulum. For spring pendulums, the period is 2 pi m over k. You can look at this and go, it is mass dependent, and it is spring constant dependent, but it is gravity independent. If you had a spring in space with no gravity, that spring would still work. If you stretch the spring, it would pull back together. If you push the spring, it would push back. A simple pendulum is definitely or gravity dependent. If you had no gravity, a simple pendulum just wouldn't work. Now, one of the things that you're going to do is, in the labs, you're going to take this and study it. You count like 20 times, and it takes 40 seconds for a 0.2 kilogram mass to do this. So in lab, you're going to take you're going to put like a 200 gram mass at the end of this spring. You're going to pull it down a little bit. You're going to let go, and it's going to go bouncy, bouncy, up, down, up, down, up, down. And one oscillation is like, it starts level, it reaches its max, it reaches its min, and then it returns to its place. Or you could start here at the top, go down, and then come back. But it's got to make a full trip. Max, min, max, middle, up to max, down to min, and back. But it has to make one full circuit. Top to bottom is not one oscillation. Top to bottom is a half. And when you're looking at this, if you could plot its position as a function of time, there's some parts that we could do. The time that it takes to go from peak to peak, the top of one to the top of the other, is capital T, or period. You could also say from bottom to bottom is period again. Both of them measured in seconds. This distance there, they call peak to peak. Or you could say peak to trough. And this or that, they call amplitude. And in physics, 2 times the amplitude is equal to peak to peak. And in when I think about this, I get very, at one point in my life, I was kind of frustrated. I was like, what's the benefit of peak to peak? We all know it's twice that of amplitude. And I can kind of look from the center line down and see what the amplitude is. Why even bother? Let's see if this shows up. Why even bother knowing what peak to peak is when I can just look at the period? Well, in terms of measuring things, the peak to peak is much easier to measure. You can kind of see where the middle line is and then measure that distance or measure that distance. And you can, there's a certain source of error, but you can tell where this thing maxes out and you can tell where this thing bottoms out, and you can more easily measure the peaks to the troughs than from peak to the center line. It's a more easily measurable situation. And then just divide by 2 to get the amplitude. So this thing is bobbing up and down, and you count, it goes up, down, up, 1, up, and up, down, up, 1, down, back to up, 2, etc. until you hit 20. It takes 40 seconds to do this with the 200 gram mass. So to find m, t squared equals 4 pi squared m over k. So k is 4 pi squared m over period squared. So this is 4 pi squared 0.2 t squared. And that t, hold on. Whoa, I need to redo this. Hold on just a second. Back this out. Never happened. Total time is n times period. Total time is n 2 pi square root of m over k. Because we don't have the individual period, we have the total time and the number of oscillations. Square it, t squared, n squared, 4 pi squared, m over k. K is n squared, 4 pi squared m over t squared. 20 m 40, and that leaves you with a spring constant of 1.97 newtons per no, not kilograms, newtons per meter. And so that's so you can get the spring constant out of this thing. In order to solve for k, the k is sitting underneath the square root. So I have to square everything. T becomes t squared, n becomes n squared, 2 pi becomes 4 pi squared, square root of m over k becomes m over k, and then solve for k. You're gonna confirm this number with this. So you're going to hang this spring from a hook or something, and you're going to measure where its rest position is. And then you're going to put a little bit of mass on it, and then more mass, and then more mass, and it's going to extend each time. Yes? Spring constant is newtons per meter. How do you want me to do a unit check on this, or is that what you're saying? Sure. Let's see. Kilograms. Wait. But what we have here, watch and learn. There is an imaginary meter over meter. The problem would be, this is not problem, an assignment. Show that kilograms per second squared is newtons per second, or newtons per meter. Because if there's an imaginary meter over meter coming into existence, you can rearrange this so that it is kilograms, meters per second squared meter. That becomes Newton, or Newton meter. Boom goes the dynamite, as they say. So, because for a second there, you sit there and go, because he was going, well, isn't it just kilograms per second squared? Well, I know that the spring constant is newtons per meter. So either A, I've done something horribly wrong. Actually, there's a third thing. B, we've invented new physics and we need to get Stockholm on the phone. Or C, we got it right, we just don't know it. And we did the third thing. We got it right and didn't know it. Because this shows that kilograms per second squared is newtons per meter. Same thing. Yes? What I did is I multiplied by 1. Perfectly legitimate to multiply by 1. It's like a unit conversion. So 1 equals meter per meter. So I just multiplied it by 1, or meter per meter, and then I rearranged stuff.
It's really the same thing. So
it's the same. It's equivalent. Yes. A kilogram per second squared is the same units as Newton per meter, even though there is no meter in kilogram per second squared. Kind of freaky. But if you just rearrange the things, it just pops right out. That's a very good question. So you have this spring. Now we've bobbed it up and down a couple of times, and we solved for the spring constant. and we're going to do it, what we're going to do is we're going to check it with this. You have a spring, it's hanging from a hook, that's the rest position. Then you put mass on it and it lowers, mark it. You put more mass, it lowers, mark it. So what you're going to do is you're going to have a certain amount of mass hanging at the end of that spring, and you're going to have a certain distance associated with that. So what you can end up doing is when you understand that F is equal to Kx in terms of the magnitudes, you've got, when this thing stretches, you have the force of the spring, which is Kx up. You've got force of gravity, which is mg down. So the sum of the forces is equal to Kx minus mg, which is equal to 0. Or Kx is equal to mg. Or what I'm gonna do is x is equal to g over k m. So let's say m1 I'd have to work really hard to get the numbers to agree. Let's say in another universe that we haven't worked with this, that mass 1 was 0.1 kilograms and the distance was, I'm trying to figure this out. Let me tell you how you're going to do this. So you're going to plot D as a function of M. The greater the mass, the greater the distance of deflection. And then you plot it out and you fit a line to it. This thing, you're going to fit the slope. That slope, now traditionally you use M, but I'm not going to get that confused with this. That slope is equal to G over K, and that K is G over slope. So what you do is you sit here and you go bouncy, bouncy, and you count the number of oscillations and you work out the numbers and you get that. And then you suspend this thing and you stretch it a couple of times so that you get a data set. And then you fit the line. The line gets fit, and the spring constant here should agree with the spring constant there. It should agree. There's another way that you can get it using the period, and that is you have the mass, the number of times that it oscillates, the total time that it oscillates, the period of that oscillation, and period squared. So you're going to put like 100 grams, 200 grams, etc., dot, 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 dot. And you're going to probably have like number of times 20 and just be 20, 20 all the way down. But the total time is going to change, the period is going to change, and the period squared is going to change. Now, one of the things that's weird is, you're like, well, why am I using period squared? The period is 2 pi square root L over G. So when you do this, this is not a line. It's a curve. Why am I using L over G? Because, good question. I'm going to use M over K. Thank you. So with this period, you're not going to get a straight line out of this. You have to quadruple the mass to get double the period. And it's not, I think it looks like something like that. It's not very straight. But if you take t squared equals 4 pi squared m over k, this is linear. And let me rearrange it so that you can see it. T squared is equal to 4 pi squared over k m. If you double the mass, you double the t squared, and you end up with a straight line. You need to plot it like this. In fact, when you do the simple pendulum, what they'll have you do is you'll plot both of those things with t squared and m and then L. And what you end up with is that the spring slope is equal to 4 pi squared over k, so that k is 4 pi squared over spring slope. And then in the other one, the simple slope, four pi squared over g. With this one, you can rewrite it like this. For the spring slope, you're confirming it with that. You're going to stretch it. You're going to have it oscillate with various masses, but the K should agree. Why? Because it's the same spring. In this lab, you're also going to confirm G. G, the gravity, you should get 9.81 meters per second squared. You will not get the 213 chalkboard value, which is just straight up 10. So what this does is it helps you understand oscillations. It helps you understand how to confirm things using different types of experiments. I understand that this can be a bit more confusing, but the computer can fit a straight line way more easily than a curved one. If it's anticipating a line rather than a curve, it can do that a lot better. So this is the lab. You guys, I think, are doing buoyancy next week, and then are you doing buoyancy? You did buoyancy this week, okay? And then simple, yeah, you're going to do oscillators next week. So this is the lab that you're going to do next week. kind of explain theoretically. Now, a couple other things that we need to talk about this wave thing. We've talked about oscillations in terms of if this is time, then there to there is period. So if you're sitting there and you're plotting the height of the wave as a function of time, so the wave comes at you, it goes up, it leaves, it goes down, back and forth. But if you were physically looking at the waves as a function of position, if you had waves going and you froze time and you looked at the waves, you would still have peaks and valleys, but this distance here is now known as lambda, as the wavelength. Wavelength is the distance physically from one peak to the next. So if you've got a peak here and you got another peak 5 meters away, the wavelength is 5 meters. And there is a relationship between the velocity of the wave, the wavelength, and the frequency. And that is velocity is equal to lambda f. That if you have two of the three values, velocity, wavelength, and frequency, and you got two of those three values, you can get the third. So let's say you were in a pool and you bobbed up and down 4 times in 16 seconds. The distance between peaks is 20 meters. What is the velocity of the wave? So if I give you the number of oscillations and the time is number of oscillations times period. So little t over big N is period, but since frequency is the inverse of period, this becomes big N over total time. So the frequency is 4 over 16 or 0.25 hertz. So that's the frequency. And you have the distance. If the wavelength is 20 and the frequency is 0.25, oh my goodness, I wrote that up. 0.25, actually what would be better is 1/4. Then the velocity is 5 meters per second. And so you can get that. You can get, if I give you velocity and frequency, you can get wavelength. If I give you wavelength and velocity, you can get frequency. It's one of those like give two, solve for the third. All right, thinking, what else? Because really what we're doing is we got to start sound next Thursday. There is one thing. It's a single problem. How bad can it be? Well, it's going to be pretty bad. But it illustrates a particular point. Those of you who are pre-med and pharmacy, you're planning on taking the MCAT and the PCAT, and there is something that they call passage problems. I didn't intend on doing problems that ended up being passage problems. It just started. In couple of years ago, I started doing what I call hybrid problems. Hybrid problems are a way they are problems that cover multiple areas of knowledge. And really, it started out as a way for me to go, well, they're learning basic physics. I need to teach them something to let them understand that we've got our normal baby physics, and then we've got a layer deeper. Now, granted, there's layers way deeper below that, but make it a little bit more complex, because I think you guys are ready for it. So what I started doing is I started piecing together, like, let's do this. You have this is a massless post. That's distance x1. This is distance x2. This is a string. This is distance y. There is a 20 kilogram mass hanging at the end of that post, or flagpole, or whatever you want to call it. What's the tension in the string? So this is basically a torque bar problem. And it doesn't look that bad. If you look at this, you choose this as the rotation point. You have a tension in the Y. We break it up into components. And really, we get this. This mass is pulling down with the force of mg. This string is pulling up and to the left because it's effectively going in that direction. So what we did is we broke up the tension into a y and an x component, because that vector plus that vector will give us that vector. This is our rotation point. That is the distance x1 and x2. On this force diagram, actually it's more like a torque diagram, you have three forces, Tx, Ty, and Mg. The rotation point being the hinge of the whole of this ball. I'll give you a hint. One of those three forces has a torque that is irrelevant. Which one is it? T what? Tx, correct. Why? It's aiming straight at the axis, exactly. If you look at this door, what's the best way to push on the door? Like that. The force that I apply is perpendicular to the arm. if I stand outside and I push on the door directly at the hinges, the arm, the distance from the rotation point to the horse is actually 0. So no torque is applied. All the torque that you're interested in is the torque that's actually perpendicular to the bar and is a particular distance from the bar. So if the force is aimed directly at the hinge, it's irrelevant. So, so when we do our sum of the torques is equal to 0, Ty x1 and mg x1 plus x2 there to there is to the right, force is up, torque out, positive, force is to the right, force down, torque in, negative. So mg x1 plus x2 is equal to Ty x1, or mg x1 plus x2 over x1 is equal to Ty. M is 20, G is 10. Let's see, x1 is 1.5, x2 is 1. So the tension in Y is 333.3 on and on. Hold on. Yes?
So the reason you're not worried about TX is because you can't move that direction?
You can't move it. If you, I mean, literally, try to get that door open if you're pushing directly at the axis. Yeah, which one can't be used? Because when you think about it, hold on. Yeah, you need to, yeah, it helps. No, we're about to get finished the part. And then, once we finish this, I'll give it as an assignment for your amusement if you want to go. The part that makes it fun. We're going to get out of here in just a few minutes. That tension is of a ratio. This distance is 1.5. I never gave y, but let's say y is 0.75. That theta there is the inverse tan of y over, really, x1. So this becomes inverse tan of 0.75 divided by 1.5. So inverse tan of 0.5 is equal to 26.6 degrees. So that's the angle that string goes up. So if you have the tension in the vertical and you have theta, you can get the total tension. Sine of theta is Ty over T, opposite over hypotenuse. So T is Ty over sine theta. That means Ty 333 1/3, sine 26.6. and I get 744.4 newtons. And that's the total tension in the string. So it's a torque bar problem, but a little bit more complex. So the assignment will be this. Rather than have this thing sitting here hanging in the air, this is made of a material that is 1,400 kilograms per cubic meter. So it has a specific density. We'll call it rebellium. This particular rebellium has a density of 1,400 kilograms per cubic meter. You take a big bucket of water and you lift it up so that the hanging mass is now descended into the water. What is the new tension in the string? I will ask for answers on Thursday. So this, now what does this do? It takes knowledge from torque and fluids and puts them together in the same problem. This is how I'm gonna get Atwood's machine into test 3. I'm gonna create a hybrid problem that we'll talk about next week. That's it, see you Thursday.